Okay, so before starting the lecture today, I want to just revisit the backdoor adjustment and explain better the front door because it was really fast last time. And so the backdoor adjustment, this was in the exercise sheet. I don't know if you have questions, but basically it's a condition, it's like a graphical criterion that you have to find a conditioning set that's the Z. So you need to, so for a pair, X and Y, so it's always relative to a pair. X and Y can be set, doesn't need to be like only one variable X and only one variable Y, but you need to find this set Z such that for every variable X in the set X and every variable Y in the set Y, Z has to block these paths that are into X. So those paths into X are called confounding path or backdoor paths. Also, the set Z cannot have descendants of the variables in the set X, right? So if you find the set Z, then the set Z is said to be or it satisfies the backdoor criterion, or it's admissible for backdoor adjustment, and then the probability of Y given to X is given by this formula. And this formula, it's so you need to memorize this constructor. It's basically a sum over Z, so Z being our admissible set for adjustment, and Z appears in the first conditional term, appears after the conditioning bar together with the X, and then you have the weighting. So basically what we are doing is getting the probability of Y given X and Z, the conditional probability of Y, X, and Z, but we are reweighting this probability by the variables, by the probabilities of Z, right? So basically it's an adjustment, or we are a weighting procedure to adjust this probability in the middle. So this is called adjustment formula. So as an example, we have this graph. So basically that is only, there are two paths connecting X and Y as a confounding path, right? That's into X. We have a causal path and two confounding paths. And Z, so only the variable Z is sufficient to block these two paths. So the set Z equals to Z is admissible for backdoor adjustment in this case, okay? I also mentioned that there are several sets that are admissible for backdoor adjustments, right? So, for example, in this case, we have either just Z1 or just Z2 or both. They are all admissible for backdoor adjustment. So you can use this formula for the minimal. So it could be either Z1 or Z2 here, or it could be both, right? So the formula is valid for, like, if you use a set that's admissible for backdoor adjustment, the formula is valid. So this is an example. I just go fast here. I don't know if there's anything interesting. So this is a case where the minimal admissible set is the empty set, right? Because the confounding path is not open, so we don't need to condition on anything. So basically the empty set is sufficient. So basically the interventional distribution is the same as the conditional of Y given X. So the observational conditional probability of Y given X is also the interventional distribution of Y given to X. So it's a case where you don't need adjustment. It's just the same as the observational conditional probability. Here's also a case where is the empty set. The difference is, so here's an interesting case, because that is the second condition where the set Z cannot contain descendants of X, right? So the empty set is valid because there's no descendant, but you cannot adjust. So in this case, Z2 and Z1 and Z2 are also admissible, but in this case here, they would be descendants, so you cannot, right? So that's the only one. And there are cases where there's no admissible set, as the last case. So Z1 is open this collider in this case here. So Z1 is open. If I condition on Z1, we open this path because we are opening this collider. And if I condition on Z2 is descendant of this collider, so we still be opening this first path. Okay, so the ones that have the minimal number of variables, they are called minimal backdoor adjustment sets. I guess no questions up to this point, right? And I told you that in causal fusion you can play with this. Basically, you can just draw the graph, and we need to fill up this line here, this part of the interface, and then we ask what's the causal effect of, for example, x on y. So you just need to type the names of the variables that you want to check the effect of, and by pressing compute, you just get the formula. So if there is a conditioning, if there is an admissible set for adjustment, it's going to appear the adjustment formula, right? That's another case where the z is still also the set with just the variable z is admissible for adjustment, and this too, so it's just symmetric, and this is a case where the effect is not identified. So this is not identifiable through adjustment, and also not identifiable at all. So the the algorithm that has in the back end of this application is the general algorithm that we are going to see later, and it runs it. So if there is other criterion or other procedure that would give us an identification of the effect, it would show. So by the fact that it's not identifiable, it's not only through backdoors, but all other criteria. And I also mentioned, I just briefly mentioned the existence of front door last lecture, and I'm going slowly now. So that's another adjustment. So it's now through this front door path. That's why it's called front door adjustment. So the criteria is the following. Let x as being the set of treatment variables and y is the set of outcome variables. And then we are now looking for a set M. M is from mediators. So instead of looking for a set of covariates or variables that are creating confounding, we are now looking for a set. We are looking for a set of variables that are now mediators. So a mediator, it intercepts all directed paths from any vertex x on the set x and any vertex y in the set y. The second condition is that there's no unblocked backdoor path from a variable in the set x and a variable in the set m. And the third one is that all backdoor paths from m to y are blocked by x. We can see in the example. And if you find this M set, then you can just write the probability of y given to x through this other formula. It's a little bit different. So a nice, I should show, maybe I showed this. I remember having some slides about it, but if you try, it's in the next lecture. So you see here that this is the effect of x on M, and that is an effect of M on Y through adjustment on X. So you can see two different parts here. Because so that's the classical front door adjustment graph. You have just one path. So my question is, what's the effect of X on Y? And you cannot apply the backdoor adjustment because the path that's confounding X and Y cannot be blocked. So there is this other criterion, that's the front door, that you can now identify the effect through this mediator. So M is a mediator between X and Y. The first condition is satisfied because M intercepts all directed paths, there's just one. The second condition is that the path between X and M, so no unblocked backdoor path from X to M. So between X and M, there is no backdoor path that's open. In the second one, if I ask you what's the effect of M on Y, you would be able to apply the backdoor adjustment here because the path that's into M is this one through X. Then X is admissible for backdoor adjustment. So it's a set that's admissible for backdoor adjustment for the pair M and Y. Then I can compute, so if you just look at this sum here, is exactly the adjustment over X to compute the effect of M on Y. Okay? And the first one, since there is no confounding path, so this path here is blocked already, see? So the effect of X on M through backdoor, but using the M set, is just the usual probability of M given X. So in the end, it's a composition of two backdoor adjustments and give us the effect of X on Y. So here in the first example, the set M is just the variable M. Now, what happened with the second graph? Simple. Huh?
I mean, I have the solution in front of me, so I'm not going to say anything.
Okay. So I need a set of variables that are intercepting the causal paths and has to intercept all of them. So what are the causal paths?
xn1y and xn2y.
Yes, so the first through M1 and the other through M2. So I need a set of mediators that are intercepting these two paths. And let's take M1 and M2, right? Now we need to check the second condition. All paths between X and the variables in M, so the first edge, X and M1, and the second edge, X and M2, so these are two paths, they have to be unblocked, so there's no unblocked backdoor path between them. Okay, so this one here is blocked, the other one is blocked. Okay. And the third condition is asking that the backdoor path is from M to Y, from variables in M to Y, can be all blocked through by conditioning on X. So this is the same as well for M1 and M2. So the set M in this case is going to be M1 and M2. What about this? Not possible. You understand why?
Because X and Y have a path.
Yes, there is no way to intercept this causal path. And what about this last one? Can go by parts. So M, let's try the M, variable M, being the only variable in the set M. It satisfies the first condition. There's only one causal path here. What about the second condition? Unblocked backdoor path. So is there any unblocked backdoor path between X and M?
Is it the cell phone?
Yes, so it's violating this. It kind of violates also the third condition because this is a confounding path and conditioning on X is opening. So you cannot apply the front door criteria to get the adjustment. You can also use the causal fusion. So this is the classical example, and if you ask the effect of X on Y, you're going to see this formula. So it's pretty simple. Later, if you have fusion already, I will recommend you to go through this menu here, so you can have the derivation option. If you click here, you're going to see how can you derive this probability, this expression here. And we are going to see in the next lecture the do calculus. So the derivation is in terms of do calculus rule. So you can see the entire derivation that's coming out of the algorithm that actually has that's running in this app. So I guess it's pretty useful for identification because first of all, you can check any graph, not only those that are through backdoor and front door. And also you can see the entire derivation through the calculus. So questions, because this ends the last lecture. Okay? Okay, that's...
Will there be today an exercise class or?
Yes, Jan is just late. Not late, he's at a meeting. Oh, you're starting the lecture now. I just finished the last lecture, so so part of the lecture today is also also reviewing the backdoor. So I'm going to skip this. So last lecture we saw the backdoor adjustment, and so I will skip this. But I want to also tell you an alternative version of the backdoor adjustment because it's just useful for when X is a set of variables instead of a singleton set. So the only difference here is that instead of blocking the confounding paths, we are now looking through this separation of of X and Y by Z. But in this graph where we use this notation here, so now is GX underline. So I told you already a notation where we have GX upper line, where we remove the edges into X. This is the other side of the manipulation where we remove the edges going out of X. So the underline is going out of X. So if you consider this graph here, the G X underline is removing the only edge that's going out of X is this one, so it's removing this edge. And to apply the backdoor criterion, we now need a separation of X and Y. So it is the same idea because once you remove these directed paths, you are just left with the confounding paths, and blocking all the confounding paths gives you the separation. So it's the same idea. But there is this manipulation, so it makes it easier when you have several X, and we are going to see examples with several X's. And the second condition is the same. So the set Z cannot have descendants of X. So now questions? Okay. So now let's see an example with two X's. So how can you apply now the condition? So we first compute the GX underline.
I don't understand. You take away all the errors that come out of X,
yes,
right? But then there are no descendants of X, right?
Now, so the descendants are defined in G. Yeah, the descendants are defined in G. So you don't have descendants in the final graph, of course, but you could have descendants in this graph.
Okay.
Right.
See, because in point 2, I think we're still in the set where the causal graph G the entire, because only for point 1 are we
looking at G.
Looking at a different graph.
Yeah, so the theorem is the same. We are just looking in a different way. So the GX underline now removes the edge that's out of X1 and the edge that's out of X2. So we don't have this edge. Oh, that's also this edge here. So we remove these two edges out of X1 and this edge out of X2. And now we apply, we try to see which set Z that has no descendants of X separates X1 and X2 from Y, right? I feel that I'm kind of blocking our vision, but basically, so X1 is already completely separated from Y, so it doesn't matter. And X2 and Y, they are connected through this confounding path through Z1 and Z2, okay? Mm-hmm. So if I just condition on Z2, it's fine. What about Z1?
Z1 is a descendant of X1.
Yes. So I didn't have it here, but it's a nice example. I would put.
Also, would it be enough for the deseparation criteria because we have Z2 going into Z1? So sure, it fails condition 2, but
Sorry, what your, I didn't understand your question.
If we went through the conditions, I mean, we have two conditions, 1 and 2.
Okay.
And we just talked about that it fails condition 2 because Z1 is a descendant of X1.
Okay.
Or that was just the summary, if I understood correctly. But Z1 alone would also not deseparate X2 and Y.
So that's why I think it's easier to see in this graph, because the path that you're talking about is this one, X1 through Z1 through X2 to Y.
Mm-hmm.
And this path is not a confounding path. It starts with an arrow out of X1. So the confounding path, there's no confounding path between X1 and Y.
Mm-hmm.
There is a confounding path for X2 and Y, which is this through Z1 and X1. And it's going to be blocked by X, by conditioning on X. This is already satisfied in the formula.
But right now I was just talking about GX underscore, so underline.
Okay.
So the first condition. So for that, Z2 is in a deseparating set between X and Y in this case.
X2 and Y.
X1 and X2 with
yes,
Y, both together.
Yeah,
both
X2 and Y. So wait, what was this? Z2, Z2 is deseparating X2 and Y. That is clear so far.
Okay.
But Z1 alone is also not deseparating. Z1 is not deseparating X2 and Y in the underscore graph, or is it?
Z1?
Yes.
It's still deseparating.
It is.
But it just can't be because condition 1 and 2 have to apply.
Yeah, I know, I understand that. I was just, for the sake of argument, going through condition 1 again, and now I think that clears it up.
Yeah,
Both
but
of them deseparate, right?
yeah, I don't know why you thought that the Z1 is not deseparating. If it's a matter of deseparating just this path, or because you are looking at this other path here.
Yeah, it makes total sense now. Yeah, I made a small mistake.
Okay.
Yeah.
Yeah, so I guess it's kind of helpful in this sense when you have like different paths, and some of them, like this X1, Z1, X2, and Y, is not actually confounding. So you basically don't see it here. So it's kind of helpful in this sense. And this is just because, I mean, it's a review from last lecture, but I did already. That's a question now. Is backdoor criterion complete for covariate adjustment? Which means like if I apply the backdoor criterion, I will always find all the covariate sets such that the backdoor adjustment would be valid. Let's just see an example. Because complete is in this sense, like for every set that I can apply, it's sound, but also, so it's a sufficient condition, but it's also a necessary condition in the sense that if I apply for one particular set and doesn't work, it's because it really doesn't work. And you see that part fails. So backdoor is not complete. And this is an example. So if I apply the backdoor adjustment, we will see that the empty set is admissible, right? So this was an example from before. No, not really, but it's similar. And the empty set works because there's no confounding path. Okay, and it's blocked, so that's fine. If I try to get, for example, X, don't know if I put this already. So no. So if I ask you, is Z1 or Z2 or both, any other set composed of Z variables, is admissible for backdoor adjustment? If I try Z1, for example. No, because?
Z1 is a child of X.
Yes, it's a descendant. What about Z2? Not even?
Yeah, the same applies.
Yes. Z2 is 1. So you cannot, right? And however, let's do the following. So I'm just applying probability properties here. So I get the this is true, right? So we just apply this. This is true. So I'm starting from this. So now I'm summing over Z1, the probability of Z1. So I'm just multiplying by 1. Okay. Then I can put the Z1, the sum in the beginning. And Z1, actually in red here, is independent of y given x. So Z1 is independent of y after conditioning on x. This is blocked, this is not. So blocking conditioning on x. So using this implied independence, I can put the Z1 here in this first. And in the end, we get the expression of adjustment over Z1. So the expression is valid using set Z equals to Z1, but it's not given through the backdoor adjustment criterion. So it's not complete, right? So there are sets where it's valid. I can go further, and let's do here. So I start from this, and I can get the first probability here, and sum over Z2. So that's the same as the first condition here, conditional. Then I move together Z1 and Z2 in only one sum, right? It's just a notation. Then I'm opening through, so that's the joint of y and Z2, so I'm just separating. So that's y given x, Z1 and Z2 given x and Z1. And x is actually independent of Z2 given Z1. So x and Z2, they are independent given Z1. Okay, so I can remove the x. From this line to this line, I'm just removing the x. Now, these two together is the joint of Z1, Z2. And this is the same. And then in the end, I again have the adjustment expression over Z1 and Z2. So Z1 and Z2 is also a set that's admissible for adjustment, but not using the backdoor adjustment criterion. Right? That's the conclusion here. So as a result, we actually have that when x is singleton, or the cardinality of x is 1, then there is always a set Z that's admissible for backdoor adjustment if there exists some set that's admissible for adjustment. So in this case, I could find the empty set. So that exists the adjustment. So the adjustment works to identify the effect of x on y, and I could find it. But this is not always true if the cardinality of x is larger than 1. So yeah, so that's just in words, right? So when x is just one variable, then we don't really need to adjust using descendants, because that was the case here. The Z1 and Z2, they couldn't be part of the adjustment set because they were descendants of x. So that's what eliminated these sets. And in this result, we say that when the x is just one variable, basically there is always one set that's not, that doesn't contain descendants that's going to be admissible for backdoor adjustment. So you always find at least one if the effect is identifiable through adjustment. But you cannot generalize this for x being a set of more than one variable.
So there are sets, and we can't find all of them, but we can find one at least.
Yes, so if x is just one variable, you basically don't need to worry too much, because you're going to identify the effect. So if your goal is the identification of x and y, you're going to find the one that doesn't contain descendants, like the empty set in this example. So it's not so concerning the fact that the backdoor adjustment is not complete. But when we actually work with sets of treatments variables, then this can be concerning, because you would be able to apply a criterion and find some conditioning set that would be that you would identify your effect through adjustment, but you cannot use just the simple backdoor. Okay. Then let's see an example with two variables, just to see this. So I think that's the same example as before. And we saw that the Z2 is admissible for backdoor adjustment. You remember, right? So it was in the previous slide. So Z2 is not a descendant of X1 and X2, and Z2 blocks the backdoor path. That's the X2, Z1, then Z2, and Y. That's satisfying the backdoor criteria. So we have this adjustment over Z2. However, we can do something similar again. So we start here with the adjustment over Z2 because of this being true. Then we sum over Z1. In P probability of Z2, we just sum over Z1, the joint of Z1 and Z2. So that's just, that's true always. And then we apply in this red here, Z1 is independent of Y, given X1, X2, and Z2. You can see here Z1 and Y. If we condition on X1, we block this path. If we condition on X2 and Z2, we block these other two paths. So Z1 and Y, they are independent given the other variables, and this allows us to put the Z1 in this first conditional. And now we have exactly the expression when Z1, Z2 is admissible for adjustment. So it is it's not admissible for backdoor adjustment, but it's for adjustment, right? So Y is not for backdoor adjustment because Z1 was a descendant of X1. However, we can actually compute the effect through this formula here, where Z1 and Z2 are making the adjustment of the probability, the first conditional here. Okay. Okay, so now that's another example. So I want the effect of X1 and X2 on Y. Okay, so it's the same notation as before. And we have two backdoor paths. So the first it's a little bit different from before. So X2, Z2, and Y is one of the paths. So that's path here is this one. And the other one is through this. So X2, Z2, Z1, X1. So this is another path. If we try to find a set through backdoor adjustment, we cannot, because Z1 and Z2 are both descendants of X1. So there's no way to block without using variables. So there is no solution using backdoor adjustment. However, we will have actually that Z1 and Z2 is admissible for adjustment. I won't do the derivation for this one. You can check on Fusion. But it's one example where you cannot apply the backdoor adjustment and get at least one set, right? You would be under the impression that there's no identifiability through adjustment, while that is actually an admissible set for adjustment. So that is concerning, at least for this graphical criterion. So the backdoor criterion is sound or sufficient, but it's not complete, right? It's that there are sets that are admissible for adjustment that's not covered by this criterion. Okay, so that's the question. Is there any other criterion where we have like completeness for adjustment? And that is. And in 2010, Spitzer is like one of the big names in causality, so they have like several papers, and he actually proposed the first version of the generalized adjustment criterion, where you have completeness. So that's the reference, you can check later, but we will need a few definitions to cover it. So the first one is proper path. So to be a proper path is just a path. So let's assume that I have a node in X and a node in Y, and it's going to be proper if the first node is in X. So X is a set, and if the first node of the path has to be in X. So a path P between a node in X and Y is said to be proper if only its first node is in X. So only the first node has to be in X. So for example, let's check all the causal paths first. We are going to separate all of them. They all can be proper, but let's check basically all of those that are directed, going from X and then to Y. So we have X1, don't know why the order, not naturally the edge would be first, but the order here, X1, Z1, and Y, so we have this one first, and this one X1 and Y, and the X2 and Y. So those are considered proper because only the first variable of this path is in the set X. So X1 and Y is just two nodes, and the first variable X1 is in the set X. X1, Z1, and Y, the first variable, which is X1, is in the set X, and the other variables, which is Z1 and Y, are not in the set X. Again, the X2 and Y, we have X2 being the set X, and that satisfies the idea of being proper. Now what about X1, Z1, X2, and Y? X1, Z1, X2, and Y. So that's the directed path here. We have the first in X, but we have the third also in X. So that's why it's not proper. Okay? If we check the non-causal path, this is the same reasoning. So X1, Z1, Z2, and Y. The first one is in X. X2, Z1, Z2, and Y, the first is in X. This also, the first is in X. So these three paths, they are non-causal because they are not starting with the, let's check here, X1, Z2, X2, X1, Z1, Z2, and Y. It's not causal because you need all the edges being directed to the same direction, right? So this is starting with an arrow out of X1, but you need all of them to be a causal path. X2, Z1, Z2, X2, Z1, so that's even a confounding path. X2, Z1, and Y, it's also a confounding path. So they are non-causal, and the first three are proper. And the last one, X2, Z1, X2, X1, and Y, so it's a confounding path, and that is a variable that in the middle that's part of the X, so it's not proper. Okay. So the adjustment criterion now reads as follows. So let X be a set of treatment variables, Y is the set of outcome variables as before, and we want the effect of X on Y. So if there exists a set Z such that for every X and Y, there is a set Z that blocks every proper non-causal path between X and Y. So it's going to be this detail, there is this proper now that matters. And the second is that no node in Z is a descendant, is a descendant of a variable in the set X that lies on a proper causal path from X to Y. So the descendants cannot be on a proper causal path. It can be descendant as long as not in a proper causal path. Okay? And I need to block all non-causal paths. It's not confounding path. So let's see an example. Oh, I put a note here that remember that the W is a descendant of itself. So the set Z cannot contain a variable in a proper causal path or a descendant of such variable. So the variable cannot lie on a path, on a proper causal path, and cannot be a descendant of any variable lying on this causal proper path. And then Z satisfies the adjustment, right? So let's just see this example. So I don't want to give you the answer. Okay, so first condition here is checking all proper non-causal paths between X and Y. So non-causal means there is some edge that's not in the same direction. So it could be even out of X as long as you have some variable, some edges coming into X, coming there in direction of the first X. So you cannot have like a completely directed path. So for example, what about X1, Z1, X1, Z1, Z2, and Y? Is this a non-causal path?
Yes.
And is it proper?
Yes.
Yes. What about, so this is between X and Y, right? So between X1 and Y, I don't see other, because X1, Z1, X2, and Y is a causal path.
It's causal and it's also non-proper.
Yes. So we don't count this. I want proper non-causal. So the one that's X1, Z1, Z2, and Y counts. Now let's start with X2. What about X2, Z1, Z2, and Y?
Non-causal and also proper.
And also proper. So that's the second path. And what about this? X2, Z1, X1, and Y?
It's non-causal, but it's not proper.
Yes. So we have just two non-causal proper paths, which are here. So proper causal paths are X2 and Y, and X1 and Y. It's missing here, but this X1 and Y is also a proper causal path. The one in the middle is not, because X2 is part of the X. So this path here is causal path, but it's non-proper.
Why is the second one not causal? The X2,
So-
Z1, Z2, Y.
So that's not causal
X2, Z1.
and not proper as well.
We are going against the direction of the arrow.
So to be causal path is like a directed path, completely directed path. So this X2, Z1, X1, and Y is non-causal.
Okay.
So, but this note here is about being not proper. And it's not proper because X1 is in the middle and is part of the set X. So that's a non-causal but non-proper path. And the other path, X1, Z1, X2, and Y, is directed, so it's causal, but it's also not proper because there is this X in the middle. Okay? Then if I ask you if there is a set Z that satisfies both conditions, so I just need that the set Z doesn't have descendants in the proper causal path, so it cannot be variables lying, cannot be X1, cannot be X2, cannot be Y. We are safe in this side, and we need to block all these proper non-causal paths, which are these two. So we can use any Z1, Z2, whatever you want, and I just need to block these two. So to block these two, X1, Z1, Z2, and Y, X1, Z1, Z2, and Y is this path, and if it's kind of already blocked, but I need this other X2, Z2, X2, Z1, Z2, and Y. And to block this, if I condition on Z2, it's fine. It's what we had before. If I condition on Z2, now I'm opening the first path. So here I can have either just Z2 or Z1 and Z2 together. Right, so empty set doesn't work, just Z1 doesn't work, Z2 works, and Z1, Z2 works. Okay, it's a bit more complicated than the other one, so it's not that famous as the backdoor. The backdoor is very, very famous, but this one is complete. So in cases where you have a set of multiple variables, it's safer to try the adjustment, the generalized adjustment criterion, if you want to try adjustment first. And why adjustment is so important, then we are going to see this later, but there is a new framework. No, sorry, it's the first one. So there is another framework that's called potential outcome framework. It started with Rubin in economics a long time ago in the 80s. And they have a completely different notations. It's in terms of potential outcomes and in terms of, so potential outcome we'll see maybe in the last lecture, but it's like these different realities where you have the probability where, so what's the probability of happening an outcome given that so you can have both intervention and also conditioning on the fact that actually happened. So what would happen with an individual if that I know that took a drug, what would happen if he hasn't taken the drug, is the third layer of causality. But instead of, so they have like this general language, which is also covered in prose causality, but most of the estimation procedures, they focus, I'm being generous by saying most, it's kind of all. So they are all focused on adjustment. So if you have a expression where even the z can be really high dimensional, like can have like 100,000 variables, they have machine learning procedures that's, for example, through propensity score or just regression, basically regression-based or propensity score-based procedures that you can estimate this from data, because it's not so trivial. But the point is they focus only on this. So if your effect is identifiable through any other formula, there is no much procedures to do. We will see here how to manually compute stuff, but this is very more like this is much more developed, like in the sense that they have much more resources to estimate under this condition. So in practice, it's safer to start with backdoor if you have multiple sets, generalized adjustment criteria, and then if you are unlucky, and then you have to go using other algorithms to see the identification through other expressions, then you go to the ID algorithm. Or you go directly to the ID algorithm, and then if the adjustment is the solution, you're going to see as well. So, but many people prefer to just, because you don't need to run any algorithm to apply this criteria, you just apply by looking at the graph. So it's kind of easier.
So we only care for the second condition. We only care about any variables that are not in X. So in our case, we only care about Y. We would check the seconds of Y. Well, no, because we specifically say no node is a descendant of a variable W, which is not in X, but lies on the proper causal path from X to Y. So in Z is a descendant of X.
Yeah, so the variable Z could contain some X's. I don't think I limited. Yeah, so in the definition, it's not limited, the fact that Z is in the set that doesn't contain X's. Z is a descendant of a variable W that doesn't belong to X and lies on a causal proper path. So that's not valid. Yes, that is clear. So this in is a typo, so it's a descendant of the variable W. Okay, so I think the idea of this slide here is just show that we are kind of opening up this black box that I told you before. We have this whole pipeline for identification, and the first algorithm that exists here is the backdoor. And I mean, we have the generalized adjustment criterion that you also just saw it. But the input that it requires is a causal diagram, right? And I would like to give you also the backdoor criterion and also the adjustment criterion when the input is a peg, because this would allow you this allows identification a completely data-driven way. You just learn the pegs if you don't have the graph. You learn from data, and then you apply the backdoor criterion or the adjustment criterion directly in the peg. Yes. And this generalization is, that's the second paper by Perkovic. I think the first paper is in 2015, but she proved completeness in 2018. And that's a nice paper where we are going to, so it's introducing the generalized adjustment criterion for equivalence classes, in particular pegs. So it's also a nice reference for you to see. So to see this adjustment in Markov equivalence classes, we again need more definitions. Let's see the first one. Now it's a possibly causal path. We are now in pegs, right? So there are these circles that are just representing possibilities. So a possible causal path is just a path that it's a path that's possible to be causal, right? So it's a possibly causal or directed path from a node X to a node Y. So it's a path from X to Y that has no arrowhead pointing in the direction of X. It's just like a directed path completely. So, for example, in this example, can you tell me which path is a possible causal path?
XC1Y, XC1, Z2Y.
Yes. Simple, right? Not very complicated. So you see the definition is just a matter of the arrowheads pointing in the other direction. So you could have circles. So a path that's completely circled everywhere is also a possible causal path, right? So these two paths are exactly the ones that you told me. The concept of edge visibility I gave you already. So it was proposed here in this context. So I'm going just to revisit, but basically you already know. So a visibility of the edge, this can be just from a mag or from a peg, but it's a directed edge. And this edge is directed, but doesn't imply that it's confounded. So the visibility is related to the fact that it could be in the original causal diagram, because now we are talking about mags and pegs, like a representation of a class of models. So in the original causal diagram, it cannot be confounded if it's visible. So it cannot have any bidirected edge there. So this directed edge, represented in a mag or peg, is visible. So there are two conditions. Or you have a node V that's no adjacent to Y, such that the V, so there is an edge between, let's just see the example directly, it's hard. So let's apply, the first condition is, there is a node V that's not adjacent to Y. I'm checking the visibility, for example, of the edge X1 and Y. Okay, so it's directed, it's the first requirement, so it's a directed edge. And the second one is that is a node that's pointing to X1, so you need this edge between V and X, in this case X1, that's into X, that's written here, and V is not adjacent to Y, which is written here. So if you remember from the FCI, it's kind of the principle that's in the rule 1. So if exists is this V not adjacent to I, when you condition on X1, it, so in the rule 1, why rule 1 works? So if you have like a variable v pointing to x, then pointing to y, and you don't know what's here. It could be even like, this is the rule 1. But the point is, you know that v is not adjacent to y, so you have, you for sure you have, you know that the x is a non-collider, because if it was, then in this case it was not even there, but then, so here you know that's a non-collider, you already have the edge. So by the rule 1 you know that's a non-collider from the rule 0. But if you have two conditions, right? If you condition on x, basically you have to block this only path between v and y, and so v is independent of y given x. And why I know that this cannot happen? Because when I condition on x, all the paths that are into x are going to open, because I'm opening these colliders in these other directions here. And if I had something like this, like a hidden confounder between x and y, this would be an inducing path. And x and v would never be separated from y, and then they would never be without an edge here, be no adjacent. So the fact that v is no adjacent to y means that there is a separator, and the separator includes the x. So when I condition on x, I cannot have any path that's open here. That's why I know that for sure it's not confounded, and this is visible, and it's even like this. So that's the principle, and that's the most powerful rule that we have, because it's not only giving us the direction, but it's giving this fact that there is no hidden confounding between x1 and y, and allow you the identification of the effect. Because if you had a bidirected edge, then this effect would never be identifiable. So that's the first condition, is being v pointing to x here. But there is, so there are two edges that are visible, x1 to y and x1 to x2. It's the same principle. So we apply both. You all can see this, right? The other condition is when...
What about the other one that was directed? It's not visible because it doesn't...
Yes.
But it's on the deck, so it's...
So this means... This is an interesting thing to reflect about. So it's saying that's not visible, because there is no variable pointing into V3. So you cannot apply. So basically what's saying here is that x3 and y can be confounded. Can you create a diagram, a causal diagram, that's represented by this peg, where V3, where x3 and y are just connected by an edge that's confounded? Could be just a bidirected, could be a directed edge plus a bidirected.
I think if we do confounding between x3 and y, that's a given, right? And then we also...
I mean, I can give you the simplest one. What about...
There's confounding. And yeah, already works.
Is this module part of that peg?
Mm-hmm.
Yeah. So x3 is ancestor of y, which is represented there, like that edge. So when you move from a diagram to a meg, this is going to be the canonical meg of this peg. So it's like automatically, like I can construct a case where x3 and y are confounded. And that's why cannot be applicable, the condition there. But this is an interesting exercise for you. Try to construct a diagram where x1 and x2 or x1 and y are confounded. We are going to find some contradiction. And then This means that the entire class, in the entire class, there's no model where x1 and y has a bidirected edge, or x2 and y has a bidirected edge. Okay?
What changes between max and pax to DAGs that in DAGs every directed edge is visible?
So in a, sorry, can you repeat?
In a DAG, every directed edge is visible.
Oh, right, it is notation, right? So DAG is the case where no unmeasured confound. There's no unmeasured confounding.
Okay.
So it's in Markovian
Okay.
case. I'm using DAG for the graphical model corresponding to Markovian models. And then the equivalence class in these Markovian models is a CP-DAG,
Okay.
right? You remember this? I gave this notation for you, right? So it's kind of obvious. If you don't have unmeasured confounding, you have
You don't have a measure.
Yes. Yes. All right. And the second condition here is about a collider path that's from V to X. So you don't need to only an edge that's pointing to X. You can have a whole collider path pointing to X. So that's an example coming here. So so we have 3 directed edges. Can you tell me why each of them are or not visible? So what about x1 and y?
x1 and y is just the first part where you have v pointing into x1 and then v is not adjacent to y.
Correct. Now the x2 and y. So the second condition tells us that there is a variable v that's not adjacent to y, and there is a collider path from v pointing to x2. So we have this condition here, so x2 to y is also visible. What about x3 and y?
It doesn't have to be a collider path.
So that's a collider path, but it's
But
not
it's not
pointing
x3.
to x3.
Yeah.
So we cannot apply the condition, and this means that this directed edge could be confounded, so it's not visible. So in this case, we have these 2 visible, but the other one is not. Okay? Okay, so there is this concept about amenability that's going to be required in our generalized adjustment criteria and is related to this visibility. So the first let's see what amenability is. So amenability is depending on a graph, could be a DAG, ADMG, or CP-DAG, or MEG, or PEG, whatever. So it's a concept related to a pair of X and Y, X treatments and Y outcomes. And we say that the whole graph is amenable to this pair if every proper possibly directed path from X to Y starts with a visible edge out of X. So the idea is kind of, I told you before that if you have any child that's confounded, we already have no identifiability. Remember this. So if you have a path that's not starting with a visible edge, it could be confounded, and then you would apply that criterion that to give you already no identifiability. So it's just preventing these cases, right? So I want, for example, to identify the effect of all the X on Y. Would be identifiable or not? No, I'm sorry, would be amenable. Is this PEG amenable for the pair x1, x2, x3, and y?
No, because the path x3, x1, and y doesn't start with the visible edge.
Yes. So it is amenable to which pairs?
x1 and x1 only? x2?
x2, no, you have this, right? So x1, so that's if it's x1 and y, it's amenable, but it's not amenable to any of them, because you have like one edge out of them that's not visible. So to be visible has to be directed. It's the first thing. So this is not even directed. So, but the directed is not sufficient. The fact that it's directed is not sufficient. So x3 in this case can be confounded. So x3 cannot be as well in this set. So the only one is x1. So the fact that there's two directed paths, so I need to check all proper possibly directed path or causal path and between x and y. And the two proper causal path between x1 and y is this path and the one through x2. They both start with a visible edge. So x1, like the pair x1 and x1 and y, it's okay. Like the peg is amenable to this pair, but not to others. I have another example. Yeah, what about this? Again, between x's and y. So I just need to check the proper causal path. So let's check x1. So x1, there is only one path. So it's okay. What about x2? There's no, that's also okay. What about x3? No. So this is okay, this is also okay, both are also okay, but nothing more. Okay, so that's a start. I can only focus on these pairs x and y's that such that the peg or the graph is amenable to it.
One question concerning notation. So taking both x1 and x2, so the third line of what you said works out, would that be a path from if x1 to x2 and then to y, or would that be something else? So
this path is not causal.
Yeah, okay, yeah, I thought so. So I just wanted to make clear I understood the notation.
Yes, so I just need to, for amenability, I just need to check proper possibly directed path or proper causal paths.
Yeah, I was just wondering whether in the last line the combination of x1 and x2 would mean that we are talking about this path from x1 to x2 to y.
Oh, no.
But this is not the case, so that was just a notation.
Yeah, so this is a set and this is a set. And when we are talking about sets, I need to check every path between one variable in x and one variable in y. So for every combinations of one x and one y, I have to check paths between all of them.
Yeah, that's very helpful. Thanks.
Yes. So another thing is about forbidden set. It's going to be related to the descendants, right? So the forbidden set relative to a pair in any of these graphical models is going to be every set W prime such that the W prime is a possible descendant of the W and the W doesn't belong to X but lies on a proper possibly causal path. It's really related to the condition that we saw in the generalized adjustment criterion. So forbidden, you be every variable that's not only descendant but it's possible descendant, because I have to prevent the case that it is a descendant, right? So if it is a possible descendant and of a W and this W doesn't belong to X but lies on a proper possibly causal path, then it's in the forbidden set. It's just the weaker possible case. Like I'm preventing any possible case where I'm getting a descendant of a variable that's descendant of a variable that's a descendant of a W line on a causal path, on a proper causal path. Yeah, don't forget the W belongs to the possible descendants of W. So in words, the forbidden set contains every variable line on a possibly proper path or a possible descendant of such variable. Are you okay with this? Okay. So example. Let's see what I did. Oops. So we have to start with the possible causal paths, right? So who are the, I'm talking about the X and Y, the pair X and Y, and I want to know the variables that are in the forbidden set of X, Y in this peg. So I need to check first the proper causal paths, proper possibly causal paths. So this is a causal path, it's just one edge. What about X, V4, and Y?
Causal.
What about this? No, right? So it's starting with an arrow into X, so anything that's the extension of this edge doesn't matter. So this also is not, right? Because it's and there is an edge pointing to V4. So the only two possibly causal path is X, V4, Y, and XY. So variables that are lying on these paths, and it's not X, so either V4 or Y, right? But yeah, so that's not X. So basically that's it, right? So it's a descendant. So for example, V4 is lying on a possibly causal path, and it's a descendant of itself. So it's part of the forbidden set. Y is also lying on a possibly causal path, and it's a descendant of itself. So it's also part of the forbidden set.
And in a way, it's also a possible descendant of V4, right?
And it's also a possible descendant of V4. So 2 reasons. So if you take what's the whole set is V4 and Y. Okay, now we can state the generalized adjustment criterion for pegs. So the set so basically it's the same as before. We have the set X, that's the treatment variables, the set Y of outcome variables, but can be in any of these models, can be DEG, MEG, CPDEG, PEG, whatever. If and only if exists, so it's a complete criterion, if exists is the set Z such that, first one, amenability. So the graph has to be amenable, in the sense that, you remember, we have every causal path starting with a visible edge. The forbidden set, so the set Z cannot contain variables in the forbidden set. So the intersection between the forbidden set and Z is empty. And we need to block every proper non-causal definite status path. If you remember, definite status is that every triplet is of a definite status. So path between X and Y. So this is like every non-causal has to be proper, but also it has to be definite status. We are going to see, you remember definite status? Like every triplet in this path is either a definite collider or a definite non-collider. Definite collider is just collider. Definite non-collider, we have these conditions. You remember? Okay. So if this exists, if the set Z exists or satisfies the adjustment criterion, then the effect is going to be the adjustment, as before. So this is an example, is our graph that we just saw it. First of all, amenability. So our set X is just the X, Y is just the Y. So we check amenability by checking all the possible causal paths, and they all have to start with a visible edge. And it's visible because we have this V1 here pointing to X, so V4, so it's no adjacent to V4, and it's making it visible. I mean, both of them are doing the process for X, are giving the visibility for X and V4 and X and Y. And those are the only possible causal paths between X and Y. Okay? Don't know if I did here. Okay, so proper non-causal paths. I'm giving you the answer, but so you have 2 possible causal paths. Basically, everything else is non-causal, but you need to check the proper property. However, we just have an X, so everything that's non-causal is going to be proper. So the first path is this x, v3, and y. The second one is this through v4, but going in the direction of v3. So this arrow is in the other direction, so it's definitely not causal. And that's it. Those are all paths between x and y. So we separated the causal ones and the non-causal ones. And they are all proper. We have just one x. So we need to check now who are the variables in the forbidden set. So variables that are lying in the possibly causal path. We just did it. The same example. So v4 and y, right? Yes. So the possibly causal paths and the forbidden set are here. So we need to find a set now, Z, that doesn't contain v4 or y, and blocks all this proper non-causal definite status. The definite status we have to check now. X, v3, and y is of definite status. Why?
It's a definite non-collider.
Yes, so it has a tail here. X, v4, v3, and y.
It's a definite collider and a definite non-collider.
Yes. So everything is like defined. So it's a definite status. So they are also, so these two paths they both have to be blocked by a set Z that doesn't contain v4 and y. Can you tell me which variable is this?
Just v3.
So with v3, we block this, and the other one is fine, right? So just v3. So damped set doesn't work, the v3 works. I think it's going to ask v3 and v4. And what about v3 and v4?
That's not allowed because v4 is part of the forbidden set, and it has to be, it cannot share anything with Z.
Yes. Doesn't. Oh, v3 and v2. It's okay, right? V2 is like out of the story.
Similar with v1 in that case.
Yes.
We don't have that.
Yeah, sorry, I just moved to the next slide. But now we have another example. And I want the effect of x1 and x2 on y. I'm already putting v here on every edge that's visible, but you can check it that there is always the simplest condition that has a variable non-adjacent to the other variable pointing to it. So for example, v3 allows the visibility of this edge, also allows the visibility of this edge. For this edge, I can use x2. x2 gives the visibility between v1 and v2. v1 gives the visibility between v2 and x3. And that's it. Right?
We are looking at x1, x2. What is our x and what is our y? Our set x and y.
So yeah, no, I was just explaining the v's, because the first condition is amenability, and to check amenability, we need to check all the proper. Is proper, right? Let's go back here. Proper. So all proper possibly causal paths have to start with a visible edge. So let's go back there. Oh, yes. So the proper causal paths have to start with a visible edge. So between x1 and x1 or x2 and y.
That isn't the case because x1 starts with a non-visible.
What's the path?
x1, x2, y.
Is this a proper causal path?
No, because it goes to x2. Okay.
So it's fine. So we need to list, so it's always good to list. Let's list the proper causal paths. I don't know if that is here. Yes. So the first one, so between x1 and y, there's none. because it's going to pass through x2. So it's going to be all non-proper. Between x2 and y, so it has to be directed. So this is not directed, but then there's only the edge. And the only path, x2 and y, has a visible edge. So it's fine for amenability. It's kind of helpful for the forbidden set as well. No? There is only this edge that's a proper causal path, and the forbidden set are variables lying on it, or descendants of variables lying on it that are not in X. So what's the forbidden set in this case? Variables that are lying on x2 and y that's not in X.
That's y.
Just y.
But v2, the relationship between v2 and y is just what was the relationship called?
It's bidirected edge. It's basically a confounding.
We can't have a causal path then.
We cannot.
Yeah.
It's a non-causal path.
Okay.
So the forbidden set contains only y. And proper non-causal paths between x and y. So this is a proper causal, but everything. So from x1 is everything non-proper. Either there's nothing into it, and there's no. There's nothing between x1 and y. So we just check between x2 and y. And this x2, v1, v2, and y, because of this, is a non-causal path, and it's proper. That is this path. Why this? Because x3 is part of x.
Okay, so it's also part of it.
Yes. I was also wondering why x. So x is part of the x3, and this path is not directed, so it's a non-causal, and it's also proper. There's no x between them. If we have like this, it's now non-proper. Right? And then we need to find a set Z that blocks every proper non-causal definite status path between x and y, which are those two. I forgot to check the definite status, but it's definite here, and x2, v1, v2, and y, it's also everything definite, so there's nothing to check. So we need to block these two paths. And the forbidden set is just y, so we are safe here. So which variables are okay to be in Z?
We need both v1 and v2 because the x3, v2, y, you have to use v2 to block it, but then it acts as a collider on the x2, v1, v2, y path, so you need v1 to block that.
Perfect. You all see this? So we need to block this path between x3 and y. So v2 is required. Once you condition on v2, this is a collider on the path x2, v1, v2, and y. So this is open now, so we need to condition on v1 as well. So the adjustment has to be both. So it doesn't work with only v2, but with both it works. I added the other one there. What do you think? V1, V2, and V3?
That's allowed.
Yeah, that's allowed. So that's fine. So that's all. I hope it's good time. For homework, it's basically, I want you to check this paper. You don't need to read it. Both papers are interesting, but the paper on the first paper here, they have 3 examples, and Perkovic has also this packaging R, GAC, Generalized Adjustment Criterion, in this BC-ALG-R package. I gave you the code using it already. But that is this function, adjustment set. I want you to play in these 4 examples. If you read the manual, it's kind of there already. So it's not that hard to do. But it's nice because you can check if the adjustment sets are, so check first of all the code and see, like run some simulations, but the examples there are showing different sets. I think they are all nice for you to check. So it's kind of a practical exercise. Yeah, Jan is going to be now in the exercise session, so he's not here, but he's going to be in the class in a few minutes. Yeah, but that's it for today. Thank you, guys.